at loop 2. Loop 2 and loop 1 we have said, loop 2 and loop 3. Loop 2 is this small loop, and loop 3 is this straight line. So loop 2 share this node and this with loop 3, because loop 3 is this red line. So loop 2 and loop 3 touch. Loop 2 and loop 4. This is loop 2. This node, and this is loop 4. So it is obvious that loop 2 and loop 4 don't touch, because this is loop 2 and this is loop 4. So we have a combination of loop 2, loop 4, not touching. Loop 2, loop 5. Loop 2 and loop 5, they share these two nodes, so they touch. Loop 3 and loop 4. Loop 3 is the straight line. Loop 3 is the straight line, and loop 4 is this, so they share this. So loop 3 and loop 4 they touch, and loop 3 and loop 5 they share this node and this node, so they touch. Now let's look at loop 4 and loop 5. Loop 4 is this one, and loop 5 is this one. So this loop 4 is this self loop here, and this loop 5. So loop 5 doesn't share any node, because this is the only node on loop 4, and these are the nodes on loop 5. So loop 4 and loop 5 don't touch. Do not touch. Two non-touching loops. Now, do you have a combination of 3 non-touching loops? Yeah, at least we don't have any combination of 3 non-touching loops. 0. So now we want to write our determinant. So don't for this example, the parts are defined differently. So unless you'll be revising using this, but the parts are defined differently. So determinant is 1 minus sum of all the combinations of two of individual loops plus sum of combination of two non-touching loops for our case here. Now, there's something I wanted to point out. Because of the negative direction, this loop gauge should have been negative. Negative, negative, negative. No, sorry. They're not negative. It is not shown. The gain should have been shown here. Sorry. They are all positive. It should have been shown whether it was negative here or positive. So it becomes 1 minus loop 1 plus loop 2 plus loop 3 plus loop 4 plus loop 5 plus combination of two non-touching loops, which is a minus now. I subtract loop 2, loop 4, this one, plus loop 4, loop 5. So this is our determinant. 1 minus sum of all individual loops plus combination of two loops. This is known as determinant of the graph. Now, we have two parts, part 1 and part 2. So we expect to have two cofactors, cofactor 1 and cofactor 2. Cofactor is simply path It's simply determinant. So I'll write first the determinant. And the same thing here. So this is just determinant. Hope I'm still connected. Okay. I was confirming whether I'm still connected. Now, we said cofactor is equal over path. Cofactor over path is equal to determinant when loops touching that path are removed. Now, so we have two paths. Let's look at path 1. Path 1 is a straight line. So, loop 1. Path 1 is a straight line. So, loop 1. This loop 1. So, they share this node and this node and this node with path 1. Loop 2, they share this node and this node with path 1. Loop 3 is this one, the straights completely. So loop 3 in the red, they share this node, this node, this node, and the output node with path 1. Loop 4 share this node with path 1. And loop 5 share this first node, the second node, and the last node with loop path 1. So all loops, loop 1, loop 2, loop 3, loop 4, and loop 5 touch path 1. So what I'm going to do is that loop 1 touches path 1. Not sorry for that. Loop 1. Okay. So for path 1, loop 1 touches path 1, loop 2 touches path 1, loop 3 touches path 1, loop 4 touches path 1, and loop 5 touches path 1. So loop 2, 4, they both touch path 1, and loop 4, 5 both touch path 1. So the cofactor is reduced to only equal to 1. Now let's look at path 2. Path 2 was this straight line, but from here we take this curve. Path 2 was coming up to here and then takes this curve. So let's look at loop 1. Loop 1 and path 2, they share this node and this node. So loop 1 touches path 2. Loop 2, they share this node and this node with the path. Loop 3 is a straight line, so they share this node, and the last node. Loop 4. So loop 4 is this one, and this is path 4. Path 2. This node, and this node. So you clearly see that loop 4, which is this one, does not touch this path. So loop 4 does not touch the path. Loop 5 is this, and back. And path 2 is this node, and output node. So they share loop 5 and path 2 share this node, and this node. So it is evident that it is only path 4. No, it is only loop 4 that does not touch path 2. It is only loop 4 that does not touch path 2. So I will make the cofactor loop 1 touches, loop 2, loop 3, loop 4 does not touch, and loop 5. So loop 2 touches, which makes everything 0, and loop 5 touches, which makes everything 0. So for here, I remain with only 1 minus loop 4. So according to Mason's formula, transfer function, because you have two parts, it's part 1, cofactor 1, plus part 2, cofactor 2, over the determinant, which is equals to part 1 is A12, A23, A34, F45. A12, A23, A34, A45, times 1 plus part 2, which is part 2 here is A12, A23, A35. A12, A23, A35 times the cofactor of that part, which is 1 minus L4, 1 minus loop 4, over the determinant, which is 1 minus loop 1, loop plus loop 2, plus loop 3, plus loop 4, plus loop 5. It's a plus, it's 1 minus and then plus, yes. Plus, I'm sorry for that, plus loop 2, loop 4, plus loop 4, loop 5. You can now express these loops, loop 1, loop 2, loop 3, loop 4, in their, these are loop 1, loop 2, in our definition, these are our loop 1s, loop 2, loop 3, loop 4, and loop 5. They may be different from what's in the notes. And this gives you a formula, the transfer function. You can confirm loop 1, loop 2, loop 3, loop 4, loop 5, and then these two combinations, this, which is this, and this. So the cofactors, you got 1, and you got 1 minus F44. 1 minus loop 4, loop 4 was F44 for our case. So the transfer function is loop 1, cofactor 1 plus loop 2, part 2, cofactor 1, 2 plus part 1, cofactor 1 over the determinant, which is the overall transfer function. I think up to there, I'm okay, and we are all okay. Now, I want to use a second, do 3 or 4 more examples. A second example, draw the signal flow diagram for the system in figure 2.4. This figure 2.4, this was 2.4. So I want to use as an example, let's use the block diagram approach for this. Choose the block diagram. We have drawn the block diagram for that. Block diagram for that example. Yeah, this was a block diagram. We'll use this one. So the first thing is that I will identify unique signals. I can call this x0 or x1. I call this point x2. I call this point x3. I call this point x4. And I call this point x5. Now I will say x2 is equals to x1 minus, this is b, minus b, x4 minus, this is a minus sign, k, x5. x3 is equal to x2 times 1 over m. This x3 is basically x2 divided by m. x4 is equal to x3 times 1 over s. x5 is equals to x4 times 1 over s. So I've defined all the signals, all the unique signals, and I've written the equations from the block diagram. Now I can just draw my nodes representing x1, x2, x3, x4, x5. I think I need more space. Okay, it's okay. I can use this space. So x2 is x1 with the magnitude of 1 minus b, x4. So this x4 minus k x5. I can draw it here, minus k x5. It's minus k x5. x3 is x2 over m. x4 is x3 over s. x4 is x3, which is this, over s. x5 is x4 over s. And I said, if this is a mixed node, you can just add 1. So that you don't really need to add. If you identify that it's an output, you don't really need to add. But for clarity, you may add. So to get the transfer function, you identify forward paths. Forward path. So if I start from here, this is a feedback path, this is a feedback. So this 2, 3, 4, 5. So forward path is only one path, which is equal to 1 over m dot 1 over s dot 1 over s, which is equal to 1 over s squared m. Loops. We have got 2 feedback loops. So we have got 2 loops. Loop 1 is 1 over m, 1 over s times b. Loop 1 is equal to negative b over m. This is loop 1. And loop 2 is this one. Loop 2 is equals to 1 over m, 1 over s, 1 over s, and this was k. So loop 2 is negative k, 1 over m, s squared, m. So loop 2 is equal to k over s squared, m with a negative. Now, and this loops touch. This loop share this node, and this node. So they touch. So our determinant is 1 minus sum of individual loops, which is loop 1 plus loop 2. We don't have non-touching loops. So basically it becomes 1 plus loop 1 is k over s squared m, and loop 2 is no, this is loop 2. Loop 1 is b over sm, b over sm, which was a negative, so it becomes a positive, and loop 2 is k over s squared m. So we have one path. One was 1 over s squared m. Number 2, these two loops touch this path. So cofactor 1 is equal to 1 plus b over sm plus k over s squared m. So these two loops touch. So this goes to 0, this goes to 0. So cofactor 1 is equal to 1. Therefore, transfer function is equal to path 1 cofactor 1 over determinant, which is equal to path 1 is 1 over s squared m over, or time is 1 over, cofactor is dot 1 over the determinant is 1 plus b over sm plus k over s squared m. If I multiply through by s squared m, I will get 1 over s squared m plus s squared m plus sb plus k. Which is the transfer function of the system. We have looked at this before. We shall look at 2 or 3 more examples. I don't know. I shall look at 2 more examples or 3. 36. We are here. Let's look at the electrical system in figure 2.7. Figure 2.7. Now, let's look at that figure 2.7 first, and then I come back to this page. Oh, LRC. LRC 6. So it is LRC. So we recall we edited the equations as E naught EL is equal to E naught plus minus, no, it's equal to EI, sorry. EI minus ER minus EC. This is just voltage, eh? E is equal to voltage. And E naught is equal to EC. So this was EL is IS over SC, no, over SL is equals to EI minus, this is I of SR minus 1 over SC, I over SC. I'm sorry for this. This is SL. This SIL. So, and our input is EI. So our unique signals, we need EI, we need I, let me put it this way. I, SI is equals to EI over L plus I R minus IR minus IR over L minus I over SC. SCL, yes. And E naught is equal to I over SC. Now, here you have different nodes. You have a node of the input, EI. You expect to get some current, I, and then get some voltage, E naught. So, I will say that I of S, I is equals to EI over S over SL. ER is equal to IR. But this is minus IR over S over SL minus I over S squared CL. So to get your current I, you need to get your current I, you need to subtract. So let me draw it here. EI, and I need to get my current I. To get my current I need to get EI, which is EI, I divide by L. This EI over L, minus, okay. Let me just use this equation so that I don't complicate. Minus EI over L minus this VR ER the first equation. Allow me to just rub. Think it's a bit confusing. This is EI over L minus ER over L minus EC over L. So I this SI SI now ER and EC. So SI is equal to EI over L, which is this EI divided by L minus ER over L. So I will subtract 1 over L, this ER, and then I'll subtract 1 over L EC, this EC. 1 over L, 1 over L EC. One over L EC. Now, how do I get ER? ER is equals to IR. So to be able to get I will have to divide by 1 over S to get I. To get I, which is I, and then I multiply by R. I multiply by R to get ER. To get EC, I over SC. So I'll have to get first I, and then I multiply 1 over SC. So this is I, and then I multiply by 1 over SC. I get E naught. So it's something like that. And E naught is the output now. So I can arrange this to be EI 1 over L, and then that node I'll get 1 over S, which is this node, and then from here I'll have a loop. There's R over L. This is R and this is L. So this R over L with a negative, and this I'll multiply by 1 over SC here. 1 over SC to get E. 1 over SC, I'll get EC here, and then I will multiply by 1 over L negative. I'll get now our output, which is EO. Which is actually identical with this. I have 1 over L, I have 1 over S, I have 1 over SC, but this is split into 1 over S and 1 over C. So this I have obtained using the equations using SI is equal to EI over L minus ER over L minus EC over L. ER is equals to I R. EC is equal to I over SC. I'll also add I is equal to ISI over S. Yeah. So these equations, we should be able to write this. You should be able to draw this signal flow graph. So after you do the signal flow graph, you are just identify forward path. Forward path. Now we have only one path. 1 over L, 1 over S, 1 over SC is equal to 1 over S squared LC. Loops. The first one is 1 over S. Oh, there's one over L here. 1 over L, 1 over S, yeah, it's okay. L is taken. So loops, I have one loop, negative R over SL. This loop, the outer loop, loop 2, one over S squared L. So it's 1 over S squared LC. And these loops touch. So determinant is equal to 1 minus individual loops, which is 1 plus R over SL plus, this is a negative, there's a negative, so this was a negative, plus 1 over S squared LC. So path I delta I over determinant is equal to, the path is 1 over LC over 1 plus 1 over S squared LC. Multiplying through by S squared LC, you get 1 over S squared LC plus S squared LC becomes SRC plus 1. This is a transfer function using Mason's loop gain. Now, we also have, I think, 2 more examples, we have 3 more examples, and I think I will rush through them so that you can end them. Another example 310, 310, yeah, this one. So this simply, because you have been given a block diagram, I can identify this as x1, no, not this point, sorry, unique signals, x1, x2, x3, x4, x5, x6, and this x7. X6 and x7 is the same signal, so but I can just put like that. So I'll write my equations as x2 is equals to x1 x2 x6. This is x2 is x1 minus this h2 times this signal, which is x6. x3 is equal to this x2 minus x5 x2 minus x5 h1. X4 is equal to G1, G1, X3. X5 is equals to G4, X4. X6 is equal to G3, X5 plus G2, X5. So with these equations, we can just draw our signal flow graph. X1, X2, X3, X4, X5, X6, and we had an X7, which is basically the output. So X2 is equal to X1 minus H2, X6. X2 is equal to X1 minus H2, X6. X3 is X2 minus X5, X4. It's H1, sorry, H1, not H4, H1. X4 is equal to G1, X3. X5, no, X4 is G1, X3. X5 is G4, X4. And X6 is G3, X5 plus G2, X5. X5. So very quickly we identify our paths. We have one path. This was a 1, and this is a 1 also because of this coefficient of X1 and X2. So this is 1, 1. I have G1, G4. So here I have two paths. I have the one that goes straight, and the other one that makes that curve. So path 1 is equal to 1, 1, G1, G4, G4, G2, and path 2, G1, G4, G3. Because of these two parts. That's from forward to in. So feedback, what do you call loops? Loops. Loop 1 is associated with this one, G1 is H. So H are supposed to be going back. I'm sorry for this. H should be reverse. So this is G1, G4, H2. No, H1. G1, G4, H2. Yeah, G1, G4, H2. Loop 2 is this loop 1, G1, G4, G3. So loop 2 is this one. G1, G4, G3. One, G1, G4, G3, H2. And we also have another loop, 3. Is this loop that goes and then like that and then comes like this. So it's G1, G1, G4, and G2. G2, H2. it is clear that these three loops all touch. Thus, determinant is equal to 1 plus G1, G4, H2 plus this G1, G4, G3, H2. This was H1. This was H1. H1 plus G1, G4, G2, H2. Now we have only two parts. We have two parts. This part and this part. So it is clear. You can see that all these loops touch. At least they share all the nodes. So all the loops touch P1 and P2. Meaning, removing all these loops from P1 and P2, you remain only with delta 1 is equal to 1, delta 2 is equal to 1. These are cofactors. So transfer function is equal to P1 delta 1 plus P2 delta 2 over determinant, which is equal to G1, G2, G4, G1, G2, G4, G1, G2. I'm just rearranging G4 plus G1, G3, G4. I've just rearranged G3, G4 over 1 plus what you have here, G1, G2, G4 plus G1, G3, G4. There's a H1 here. There's a H1. It's a H1. H1 plus G1, G4, G3. So G1, G3, G4, H2 plus G1, G2, G4. G1, G2, G4, H2. Two more examples remaining. Just look at it shortly. The next example is this one. Now, I can identify various signals here. This VI, and call it this V1, V2, and V0. So I1 is equal to V1, VI minus V1. No, let me just for clarity, let me call it this V2 and V3. V2, V3. So I1 is equal to V1 minus V2 over R1. And V2 is equal to I1 over SC1. Is the current times this impedance, which is 1 over SC1. I2 is equals to the current through this resistance, which is V3 minus V2. Minus V2 over R2. And this V3 is the voltage across this. I'm sorry for this. The current going through here is I1 minus I2. So this I1 minus I2 over SC1. But the current through here is only I2. V3 is equal to I2 over SC2. And V0 is equal to V3. I could have as well split this as R1, V1 over R1 minus V2 over R1. And then, this was, I think, this is a question, yes. But this is a block diagram. So we want to get the transfer function of this. To get the transfer function of this, I will now write the unique signal. The first signal is VI, followed by I1, followed by V2, followed by I2, by V3, followed by V0. So I1 is V1 over R1. So V1, VI over R1, 1 over R1, minus V2 over R1, minus V2 over R1, 1 over R1. V1 over R1 minus V2 over R1. So I've done to this equation. V2 is 1 over SC1. V2 is 1 over SC1 I1, 1 over SC1 I1 minus I2 over SC1. So this I2 becomes 1 over SC1 I2. So minus, I2 is V3 over R2, V3 over R2 minus V2 over R2, which is, this is V3 over R2, this I2, so V3 over I2, R2, it should be V2, sorry, V2 is this voltage minus this voltage, is the one driving this current, so it's V2 over I2 minus V3, so it's V2 over I2, 1 over R2, minus V3 over 1 over R2. And V3 is 1 over SC, I2 over 1 over SC2. So this I2, I multiply by 1 over SC2. And V0 is equal to V3. And I believe this is what you have in this page 29, page 36. I'm just confirming that that's 7. Yes. See this. 1 over R1, negative 1 over R1, negative 1 over SC1. That is exactly the same, Same with this 29. Yes, this is exactly the same. And we can get the transfer function by saying we have how many paths? We have forward path. Forward path is 1 over R1, SC1, 1 over R2, SC2, which is equal to 1 over S squared, R1, R2, C1, C2. Loops. Loop 1 is this loop 1, 1 over SC1 R1. Negative 1 over SC1 R1. Loop 2 is this one. 1 over SC1 R2. 1 over SC1 R2. Loop 3 is this, the third one, 1 over SC2 R2. 1 over SC2 R2 with a negative. Non-touching loops. This loop, the first and the last don't touch. So non-touching loops. Non-touching loops. This one and that one don't touch. They don't share a common node. So it becomes 1 over SC1 R1 dots 1 over SC2 R2. All these loops touch this path. So the cofactor will be the determinant minus all the loops touching. Therefore, determinant is equal to 1 minus individual loops. 1 minus the sum of individual loops, which is basically plus 1 over this loop 1, SC1 R1 plus 1 over SC1 R2 plus 1 over SC2 R2. So, no, there is non-touching loops plus this 1 over S squared C1 C2 R1 R2. Because you have a set of non-touching loops. Now, P1 delta 1 over determinant. So P1 is path 1. And if I remove the loops touching this path, the cofactor 1 will be equal to 1. Therefore, P1 cofactor 1 over determinant is equals to, this is the forward path, 1 over S squared R1 C1 R2 C2 over 1 plus S, 1 over S C1 R1 plus 1 over S C2 R2 R1 C1 R2 C1 R2 C1 R2 plus 1 over S C2 R2 plus 1 over S C1 C2 R1 R2. I can multiply the numerator and the denominator by S R1 C1 R2 C2. So this will cancel and this will cancel. So it becomes 1 over S squared, sorry, S squared is S squared, yes. S squared C1 C2 R1 R2 plus, so the S C1 R1 cancel, so this becomes S C2 R2 plus C1 R2 cancel, so I'll remain with S C2 R1 plus 1. Multiply. S squared R1 C1 R2 C2. So I get this solution. Which is the same as this, S squared C1 C2 R1 R2 plus this as groups plus S R1 C. There's a term I forgot. There's a term. This is this. This is 1 2. I forgot this. I forgot this or this one. So there's S R1 C1 plus 1. I forgot these are 1 2 3 4 5 terms. S R1 C1, which is this, plus R1 C2, which is this, plus R2 C2. So overall transfer function is 1 over S squared C1 C2 R1 R2 plus S R1 C1 plus R1 C2 plus R2 C2 plus 1, which is, you can confirm with the what you have up there, should be identical. Finally, we have a last example. So this is the same as this. Finally, we have a last example. I like to do this because it's a bit interesting. Now, parts. P1. It is this. You go forward, you go forward, you go forward, you go forward, you go forward. So we have one path, which is G1, G2, G3, G4. This feedback, this feedback, this feedback, this feedback. So the other path is this. So path 2 is equals to G1, G3, G1, G5. G1, G5. Loops. Now allow me, I'll delete the parts, to become clear. Loop 1, G1, H1. Loop 1, G1, H1. With a negative, Loop 2, and call it G3, H2. Loop 3 minus H4. Loop 4, I have this path. Loop 4 is this one. It's G1, G2, G3, H3. All of this with negative signs. Clearly, non-touching loops. Loop 1, loop 2, and loop 3. So loop 1 and 2 don't touch. Loop 1 and 3 don't touch. And loop 2 and loop 3 don't touch. So non-touching loops. Loop 1 and loop 3 becomes G2, G1, H1 times G3, H2. The other one is 1 and 3, which is G1, H1, H4. And now loop 2 and loop 3 is G3, H2, H2, and H4. Now, The interesting thing about this is that we also have 3 non-touching loops. L1, L2, L3 do not touch. Therefore, 3 non-touching loops becomes G1H1, G3H2, and H4. So this is negative, negative, negative. So there is a negative sign here. So our determinants, 1 minus individual loops, plus 2 non-touching loops, or the combination minus 3 non-touching loops, which I can write it here as follows. It is 1 determinant is